Welcome to the lecture in Philosophy of Science. Last time we spoke about the testing for truth of statistical hypotheses, the method of acceptance intervals and confidence intervals. So our example was the test of a statistical hypothesis which says that 80% of all A's are C's, where A means being a tree on besides a motorway and C means being sick. So 80% of all trees besides motorways are sick, and we do this by the method of acceptance intervals. We take an A sample, 100 trees besides motorways, and we find 75 C's. So, and I told you that in order to evaluate whether this rejects the hypothesis or does not reject it, we choose an acceptance coefficient, usually 95%, and compute from the sample size 100 and the acceptance coefficient 95%, the so-called acceptance interval, which is in our case 80% plus minus 8, namely from between 72 and 88 C's out of 100 A's. And if the observed sample frequency of C's in 100 A's lies within the acceptance interval, we say, well, the hypothesis is not rejected by this observation. It is weakly confirmed. So the situation is that we assume in this test, it is called test statistics, we assume the hypothesis is already confirmed, has already been confirmed by other scientists, for example. There is some other evidence speaking for the hypothesis, and we are asking whether we have enough reason to reject the hypothesis. And if there's an observed sample frequency, which in our case is 75 C's out of 100 A's, if this sample frequency is within the acceptance interval, it's not rejected. But if it's outside of the acceptance zone, in the so-called rejection interval, then this hypothesis is strongly disconfirmed, and according to this method, it's the standard test method in statistics, which goes back to Fisher. According to this method, it is then preliminarily rejected until there's no further evidence which changes, which tells us that the true sample, that the true frequencies are maybe different. As long as there is no evidence to the contrary, the hypothesis is rejected. Okay, so in our case, 75 out of 100 lies within the acceptance interval. So according to this explanation, I showed you a picture, this one. Here you see, right, the probability distribution of the possible sample frequencies of sick trees among 100 trees besides motorways, assuming that the hypothesis that in the population of all trees in Europe, 80% are sick of all trees beside motorways, 80% are sick is true. So 80% is the true population frequency. Then the probability distribution of the sample frequencies has this shape. It has one peak. The highest value is that value where the sample frequency coincides with the population frequency, 80, that's clear. But of course, as I told you, since you are drawing random samples, of course there's a probability that certain random deviations in the samples will occur. So sample frequencies which deviate from 80% are also probable, but their probability sinks and goes down. Even here the probability is not really zero but small, so the probability to get a sample with 40% out of a population with 80% C's is not zero but it's very small. And now the acceptance, under that distribution curve, the whole area under the distribution curve is a total probability, which is 1 or 100%. But the gray shaded area here, this is an interval of 95% most probable sample frequencies. And if the actually observed frequency, you say, lies within this gray zone here, you have not enough reason to reject the law or to refute it, to say, no, we do no longer believe in this. But if the sample frequency lies outside of this acceptance interval, which is this white area here, 2.5% on the left side and 2.5% on the right side, then you reject the hypothesis, because then you say you have the result that the observed, given the assumption that the hypothesis is true, my observation has a probability of less than 5%. This probability is also called, by the way, the likelihood, right? So the likelihood of my observation is less than 5%. So I do not believe in this assumption, in this hypothesis. This is a method of acceptance and rejection intervals. Of course, you might, the first question which arises is, why do you choose this acceptance coefficient as 95%? Why not 99%? Well, if you choose it 99%, then even less hypotheses would be rejected. So a hypothesis would even not be rejected if the sample frequency lies somewhere here, right, within the, say, 98% interval, right? So this would be a very weak, very weak criterion of rejection then. But you may also ask, why don't we choose it like 50% or so, right? What is if the sample result is here? So if the sample result lies within an interval of likelihood of, say, 60%, and assume it lies outside the 60% interval, so the probability of observing a sample frequency within this interval is less, say, than 40%. Why don't we reject the hypothesis already then, if the sample result is somewhere here, right? There's a reason for that, because we are in the situation of test statistics, and we know that there are always random deviation here, and we assume that the hypothesis has already some confirmation. If the sample result lies somewhere here, then we can always, so if we are in such a, so to speak, possibly intermediate cases, I mean, there are certain theorists of statistics who recommend to have some kind of abstination intervals, right, where neither accept nor reject, which are somewhere here, right, or these boundaries here. But the point of the standard statistics is, you can, if you have cases which are close to the rejection zone but still in the acceptance zone, right, let's call them borderline cases. Suspicion cases, where you have the suspicion the hypothesis might be false. You can always clarify the situation by increasing the sample size, right? Because there's a law saying if the sample size increases, the acceptance interval shrinks and the curve here gets steeper and steeper. Let me draw that in form of the picture. So you have this picture here. So here's your conjectured true hypothesis, the value of the true hypothesis. So now, say for a sample size of 100, you have this distribution of frequencies, but if you go to 1,000, it's already that, right? So the acceptance interval gets much smaller. Actually, there's a formula, the following. The acceptance, the breadth or the width of the acceptance interval is proportional to 1 divided through the square root of the sample size n. This is a law, the general law. So if you go from a sample size from 100 to 1,000, the acceptance interval shrinks by a factor of 1/3, approximately 1/3, right? So the square root of 10 is 3.3 period, so it's something like 1/3. And this is a nice thing about this method. So if you, for instance, find a value, so here's the acceptance interval of a sample size of 1,000 is here, the acceptance interval of a sample size of 100, say, is here, and you find now a value, say, which is lying here, right? It's an actual observed frequency. So it's still not enough to reject the hypothesis, but you're somehow uncertain. Maybe the true value is really somewhere here and not here. Then you just go to a higher sample size, like that here. Now this value is outside of the acceptance interval. So if this deviation was random, with a new sample size it should lie somewhere here. But if this deviation was not random, it would then be outside of the acceptance interval of the sample with a larger sample size. And this is the rationale behind these statistics, these standard methods in statistics. Some Bayesian critics of statistics, of these statistical methods, often ask, why do we have these coefficients? I mean, why don't you compute a Bayesian and posterior probability out of a prior probability? But the rationale of this method is that you make very weak assumptions. You are not dependent on a particular prior probability or something, right? You have certain very rough criteria because you don't want to make so many assumptions. You have very weak assumptions. You know, if it's outside of the acceptance interval, you have reason to reject it, really reason to doubt that hypothesis, right? And if not, well, if it's in the borderline, increase your sample size. So that's a rationale behind this practice. Okay. Good. Still, there's one more thing to add here. According to this criterion, so if you have a sample size of 100 and we have now a value, in our case, right, let's go back to this case, the true value lies here at 75. So the true value of 75 out of 100 does not reject, does not refute, the hypothesis 80% of A's are C's, of trees beside motorways are sick. But we said this hypothesis is only weakly confirmed. Why? Why? Because many other hypotheses are also confirmed are also not rejected, so to speak, by this observation of 75 sick trees out of 100, right? Namely, all hypotheses, all population frequencies for which the observed sample frequency lies in the acceptance zone, right? And if you calculate the interval of these population frequencies for which the observed value lies in the acceptance zone, you get what is called the confidence interval. So the confidence interval is the interval of those population frequencies, or those conjectured population frequencies, for which the observed value, in our case 75 of 100, does not reject the hypothesis. It's compatible with it. The notion of confidence interval is important in the situation which you call inference statistics. Here you assume you just have the observed sample frequency and you don't have any background knowledge, right? So it's not the case that, like, for instance, if you do coin tossing, if you do 100 coin tosses and you have 60 heads and 40 tails, you don't conjecture, well, the coin is somehow biased or whatever, right? You have already evidence for the hypothesis that the probability is 50% because the coin looks perfectly regular, etc. But this is a situation of test statistics. But in inference statistics, you have no idea about the true probability. Everything may be possible. So you only have the observed frequency of 75 of 100, and then you compute the confidence interval, which is the interval of those population frequencies for which the observation would give you no reason to reject it. And this interval is simply calculated simply by drawing the width of the acceptance interval around the observed sample frequency. So now you don't draw this plus minus 8, which is the width of the acceptance interval for a sample size of 100 plus minus 8. You can compute it. You don't draw it around the population frequency of 80%, but now you draw it around the observed sample frequency, which is 75. And this gives you the interval of 67 to 83. So so you say, according to my statistical observation, to my sample observation, between 67 and 83% of trees in the population are sick, of trees beside motorways are sick. And this is the confidence hypothesis, the confidence interval hypothesis, and it is this hypothesis which is really strongly confirmed according to the statistical methods. Right? What is strongly confirmed is the confidence interval law. The probability of C given A lies between 67 and 83%. Okay, so this is a method of acceptance and confidence interval. Any questions so far? Yes?
If the observation lies outside the acceptance interval, you said this strongly disconfirms.
Strongly disconfirms, but it's not the falsification, yeah. Right? Because there's a probability of, by chance, a probability of less than 5%, by chance, to get such a strongly deviating random sample.
So I have now claimed that depending on our prior belief in the hypothesis, this might give us some indication on whether we should further investigate this, whether the hypothesis is true or not. For example, if there's we suspect a correlation, and then we do some experimental testing, and the correlation, we can't find the correlation, our results outside the acceptance interval. But we really believe, for some theoretical reasons, that this correlation should be there, then we might think, okay, it's more likely that this is a chance than our hypothesis being wrong. So let's do further investigation.
Yes, that's probably true, right? But I mean, there's no need to go to prior probabilities. You can do this, you can do it, but the question is from where the prior probabilities come, where they come from. I mean, if they come from pure suspicion or from superstition or whatever my prior probability that God exists, there's a difference whether they come from such simply beliefs, subjective beliefs, or whether they come from other evidences, right? And there is a principle which of course you should always apply, the principle of total evidence. So it could go in that direction. So if, right, there's a lot of other evidence of other experimenters in favor of the hypothesis, and your evidence speaks against it, you can collect the evidence into the total evidence pool, right, and see, right, what is now the result, the accepted, where does now the result lie, right? If the sample frequency pooled over all these evidences, is it still in the acceptance interval or not? And this is also the reason why if you pool evidence, these samples, then it may well be that in one sample the value lies outside of the acceptance interval, but you pool it together with two other samples, it goes again inside the acceptance interval. And a method in meta-analysis, you do exactly this. You pool together the results of different studies and then see what is the outcome. You have to rescale often, you have to rescale the variables into a joint format, but then that is what is the outcome. This is one way to go. And the other way to go is, of course, to go for Bayesian. Then you start with some prior distribution about the space of hypothesis, and you compute a certain posterior distribution then. And of course, if your former conjecture has a low probability, well, it depends on the prior then. But given that this prior is determined by some other evidences, you can well replace this Bayesian method, just go for the principle of total evidence and apply this, you know. I mean, an assumption of a prior distribution is always a very rich assumption. And that is a problem too, because there is a subjectivity in it. An assumption about just acceptance or rejection coefficients is a very simple, poor assumption. Okay, good. Thank you for the question. I'd come now to the second thing. Testing for relevant, the method of significant difference. So far we tested only for the truth of the hypothesis, 80% of all trees beside motorways are sick. And in the situation of inference statistics, we were interested in the truth of a hypothesis whose truth is as probable as possible, and we ended up in the confidence interval between 63 and, what was it, 67 and 83% of all trees beside motorways are sick. But now we want to know whether growing beside motorways is a relevant factor, right? It can well be true that, say, 80% of all trees beside motorways, or say 75% of all trees beside motorways are sick, whatever the true value is. That may be true, and still it may be totally irrelevant, because being at the side of motorway is no causal factor for the sickness of trees. The sickness of trees may be due to another cause, maybe to some kind of beetles or whatever, or to some kind of smoke coming from industries, or to some kind of global meteorological influences. We don't know that, so this is still open, this task, test for relevance. So how do we test for relevance? By the method of significant difference. As I told you, you have to take now an A control sample. This is, in the simplest case, a sample of 100 non-A's, 100 individuals of your population which do not have the property A, which you now test for predictive or causal relevance. So you take, in our example, 100 trees, randomly collected all over Europe, Central Europe, but not being beside motorways. But the other factors should spread, right? Should be distributed. So some coming from rural areas, some coming from areas which are close to cities, but not besides motorways, and so on. So now assume you have taken such a sample of 100 non-A's and you found 60 C's. 60 of 100 are sick. So the difference is now between 60 and 75. Is this difference reason enough to say that A has a statistical effect on C, right? It's still not necessarily causal. We will see the difference between statistical correlation and causal correlation, the possibility that there is a difference here. We will speak about that soon. But it might be causal. I mean, if there's no correlation, then it is certainly no causal either, right? So. But the question is there a statistical correlation between A's and C's, right? Between growing up beside motorways and being sick for trees. So we found this difference between 60 and 75%. Is it enough to say this is relevant, or may it be that this is just a random fluctuation? And this gives you already the key idea of the method of significant difference, right? Which is used in statistics. Because, you know, assuming that A plays no role for C, assuming there is no correlation in the population, then if you take two samples, there is of course a random fluctuation between their proportion of C's, right? If A plays no role, then 100 A's and 100 non-A's, that doesn't play a role. But there is a chance, a random chance, for having a frequency, for having a certain difference between two random samples, right? That's like the chance, assume you make 2 rounds of 100 coin tosses. What is the probability that the difference, right, of heads in your 2 rounds of 100 coin tosses is something like 15 in that case, right? It's 15, 16, 17, it's 15. What is the probability of that? You can compute this probability, right? This is a key idea now. And if the probability is low enough for finding that difference, right, as a random difference, as a result of a random deviation, then you say this is a basic idea, there is a significant correlation. And if not, then not. So, here's the precise thing. Here's the probability distribution of the difference, right, between the frequencies of C's in a sample of 100 individuals, under the assumption that the factor A plays no statistical role. So the probability of C given A equals the probability of C given not A, right? So of course, the highest probability has the difference 0, because I mean they come from the same population, so the frequency of the population is the same. So with the highest probability you expect there's no difference, but of course differences are possible, and the probability goes down and down. It has again such a approximately normal distribution. And again you compute these acceptance intervals and the rejection intervals. So here, the 95% interval lies between -13 and +13. This is what you can compute. You now compute it from the estimated standard deviation of the two samples which you compare, 75% and 60%, which compare these two. This makes a difference. And you can derive a formula from the approximated normal distribution for that difference, and you get, compute by that formula, that the 95% of the most probable differences lie over the interval from -13 to +13. So this means if you find a difference between the A sample and the A control sample which exceeds this significant difference, so this threshold, you say there is a correlation at a significance level of 5%, right? A significant correlation. The rationale behind this is, again, in that case, your observed result, assuming that there is no correlation in the population, would have a chance of less than 5%. And then you don't no longer believe in this hypothesis that there is no correlation. The hypothesis that there is no correlation is also called in statistics the null hypothesis, and we call it the irrelevance hypothesis, right? So don't believe in the irrelevance hypothesis or in the null hypothesis any longer if the observed difference exceeds the significant difference. If it does not exceed it, then if it does not exceed it, then you have not a reason strong enough to reject the null hypothesis. So then you say it's not enough reason to accept, right, the relevance hypothesis. It must exceed the significant difference. Well, that's it. And again, you may ask, of course, why do you choose the significant coefficient exactly at 5% again? I mean, why do you do that? And the answer is again similar, right? Of course, you might, for instance, choose a significance coefficient of 1%. I mean, often you find, I soon speak about that, right? Often you find correlations, differences which are far outside the significant difference, which exceed the significant difference by far. Then they may lie somewhere here, and then you say they are, say, for instance, significant at the significance level of 1%, right? This is called highly significant. Well, but you may also ask, why don't you choose a significance coefficient, say at 25%? But then we have again the situation that you must know that there are always random fluctuations. There are some small deviations. Even in the population, there are certain trampolines, right? And if you, at least if you have a high sample size, then it might easily be, right, that some group of scientists get a difference between two samples, A and non-A sample, which lies somewhere here, right? So you don't have enough reason to definitely set up a new statistical correlation hypothesis if the difference does not exceed this threshold. But what you do in that case is, again, you increase the sample size. And then you have the same effect as I explained before. Right? If it's really significant, then it lies with a higher sample size outside of this. I mean, you can increase the sample size, or actually what is even better in scientific practice, another group of scientists just replicates the experiment, the study. And if that was a random effect, right? Then they won't have it. Sorry, if that was a true relevant effect, then they will have it outside of their acceptance interval. So they will have it exceeding the significant difference, right? Okay, let's go first back to the canonical formulation. So the test, the method of significant difference goes as follows. Taken a control sample, just repeat it, 100 non-A's in the simplest case. You find 60 C's. Choose the significant coefficient, usually 5%. From the sample size and the significant coefficient, you calculate the significant difference. There's a certain formula how to do that. In our case, 13 out of 100, plus minus 13. Then you look, does the actual observed difference between the A sample frequency and the A control sample frequency of C exceed the significant difference? Is it larger than that? If yes, the relevance of A for C is strongly confirmed. You then have what is called a significant correlation, and the correlation is positive, right? If the frequency of C's in the A sample is higher than the frequency of C's in the non-A sample, and is negative if the frequency is lowered, right? In our case, it's 75 minus 60, so 30. Sorry, I had here not 40 but 60, which is 15, and this is greater than 13, so it's significant, the correlation, right? Thus this is a standard method. If no, you say the relevance of A for C is disconfirmed. It's not clear whether it's really you can really say it's strongly disconfirmed in that case. So I put it in brackets here. You say it is disconfirmed, right? So this is a method of significant difference. Okay. Again, let me go back to this curve where you have the distribution of the differences between the two samples, the experimental sample and the control sample. Yeah. First, let me repeat just the definition. The significant difference is that threshold which is exceeded by the difference between the A sample frequency and the A control sample frequency, with the probability equal to the significance coefficient, given the null hypothesis is true. So given there is no statistical relationship between A and C in the population. Or an alternative formulation in square brackets here, which is not exceeded with the probability of 1 minus the significance difference. So which is exceeded with the probability of 5%, or which is not exceeded with the probability of 95%, right? Okay. Good. So this is a distribution. Again here, you have the effect that if you increase the sample size, this curve gets steeper and steeper, and the significant difference gets smaller and smaller. That's very important. With a factor of 1 divided through the square root of n. So if you go to a sample size of 1000, you have 1 divided through 3.3 period, right? A shrinking factor. So it shrinks by more than 1/3, or by 1/3, more than 1/3. And this is very important. Why? Because, and this is a confusion which is often going on when people read reports about experimental results about significant correlations. If you have a highly significant correlation found by your study, say a difference which is somewhere here, significant at a 1% level, highly significant. This does not mean that the correlation itself is high. It just means that the probability that the difference between the two samples is due to a systematic effect, due to a correlation in the population, and not due to a random effect of the sampling procedure, is high. So significantly high correlation means there's a high probability that there is a correlation, but not that the correlation is high. Recall what the correlation means. The correlation is measured by a correlation measure, in the simplest case, the difference between these two probabilities, right? The probability of C given A minus the probability of C given not A. That is the correlation, right? You call this also the effect size in statistics. If you divide that through the standard deviation, you get exactly the measure of the effect size. But the point is, due to that law, that the significant difference is increased by going to high sample sizes, very small effects can become and will become significant for high sample sizes. So this is a crucial point. And you know, in medicine, for instance, there's a discipline called evidence-based medicine. This discipline was just a result of the development that medical scientists started to take statistics seriously, right? And they have to take it seriously because earlier several mistakes were happening. For instance, in many medical studies, they have very large sample sizes. For instance, if you read in the newspaper that the correlation is found between eating sausage and an increased frequency of cancer, right? For instance, you find that cancer patients have a higher frequency of eating sausage than non-cancer patients in their life history. What does that mean? Highly significant correlation. It doesn't mean anything. It doesn't mean that there's a really high effect size. If you have 2,000 patients, then maybe the difference between getting cancer, the frequency of getting cancer among people who eat sausage, among people and those people who don't eat sausage, is very little, maybe just 0.5% or less. And still it's highly significant because we have such a large sample size. But now if you take into account what I will say about causality in statistics soon, namely that there are always hidden variables which may cause correlations which are not due to causal connections, then small effects have almost no meaning. I mean, small effects that can have causes of all sorts, right? I mean, even the two population frequencies somehow trembling. There are all kinds of disturbing factors. It may change in time and so on, right? There is always a difference whether you draw samples, say, in the southern part of Germany or in the northern part of Germany. So you can really exclude small effects, right? So you shouldn't take small effects very serious. But exactly that is done if you go to large sample sizes. And this is a very important lesson from statistics, which is now also considered in evidence-based medicine, right? So the upshot of what I'm saying is this. If you read about a highly significant correlation, this does not mean that the correlation effect itself is high. It may be very low. Look at the sample size. Only if the sample size is small, a highly significant correlation also implies that the effect size must be not too small, must be at least moderate, right? And for instance, in psychology, people go for non-stratified experiments where you have only one variable to be tested, right? You have only one kind of connections. You go for sample sizes between 30 or, say, maximally 100, but not more. Only if you have stratified experiments where you have several variables to be tested, right? Say you have 10 variables, then you have 10 times 9 possible connections, 90. So then you might have to divide, right, your total sample into, I don't know, depending, say 10 subsamples or even more. Then you have to go to large samples because you have to consider so many subsamples. And each subsample has at least to have a size of, say, 30. Then you have to go to high sample sizes, but not for simple investigations. Okay. So this was an important point to be added to the method of significant differences and significant correlations. Any questions so far? Yes.
Are there different significance coefficients used in different domains? Between physics, let's say, and just the sort of starting level of a significant coefficient? Physics and chemistry, or different parts of physics? Or
not really, no. They are not domain specific but design specific, I would say. I mean, these statistical laws are even independent from the size of the population. All what is required that the size of the population is several powers of 10 larger than the size of the sample. And so they are not really domain specific, this criteria. But of course, it may depend on the design of the experiment. So, for instance, if you have an experiment which consists, like in brain scanning, which consists of several of a sequence of simple experiments in each element of the sequence. In each step of the sequence, you draw a sample and look for a significant correlation. Then, for instance, there is a large probability that some of these correlations in the sequence will be wrong, will be just faked random correlations. Yeah? And then there are certain methods which you have to apply in addition. Then if the total result out of the sequence of experiments is evaluated, you have to apply certain additional statistical calculations which would exceed the content of my talk, of this lecture. There are certain methods then which you apply. But the basic statistical laws are the same. There is no domain dependency. If it's a random procedure, then there's the central limit laws and the laws of error distributions are always the same. Any further questions? No? Okay, then let's speak about further thing. We said that the samples must be representative. So the requirement of representativity has to be discussed. The sample has to be representative. What does that mean? Well, that could be well, that's really nice. I can write down more careful. Representative sample. So here we must distinguish, and that is philosophically important, between the definition of representativity and the criterion. And what is important in practice is the criterion and not the definition. I mean, the definition is important too. The definition says that a sample is representative in regard to a certain conjectured correlation between two factors A and C, if all other factors besides those two, which may be of relevance for the criterion variable C, if all these other factors, call them remainder factors, if all the remainder factors are distributed in the sample as they are distributed in the population, right? So if we estimate, say, the correlation between heart disease and eating sausage, right, then there should be 50% male and 50% female persons in the sample, because we know 50% is the value of this remainder variable in the population, right? And it may be that the sex, the gender plays a role, the sex plays a role for heart diseases. Actually it does, as we know. So this is a definition. of representativity. But of course we cannot apply the definition in the situation where we don't have background knowledge. I mean, the definition presupposes already that we know all the true statistical correlation in the population. Sometimes we know. If we know it, if you know them, then the situation is different. But if you don't know, then we cannot apply this definition. So we need a procedure by which we can produce a representative sample, at least in most cases, at least in many cases. And this is a procedure of, and this is a criterion of representativity, random sample, right? The random sample. Random sampling means that we draw the elements of the population by random, right? We ignore all attributes, we draw them blindly or in some way, so that those attributes from which we may assume, from which they can at least be a suspicion that they may be relevant, all of those attributes are ignored in the process of random sampling. That's the idea of random sampling. In the ideal case, I blindly draw a ticket from a big urn. Right? From a big urn of 10,000 individuals, I draw 100 of them. Right? That is the paradigm of random sampling. But of course, actual procedures of random sampling might not be of that sort because it's not practically possible. But you still, the idea is always the same. You ignore each individual must have the same chance to get into the random sample. That's the idea. And from this idea of random sampling, you compute and you derive all these statistical laws which I told you, all these distributions of population frequencies, right? You compute from this idea the idea of a binomial distribution for discrete variables, right? The binomial law, or the Gaussian normal distribution for continuous variables, the error distribution, and so on. Of course, if you have a rich background knowledge, you can do better. For instance, in the case which I told you, where when you prepare a sample for a study with human people, like influence of food habits on their health, you know, in the population there are 50% male and female, so you know this already, and so you put 50% male and 50% female on purpose into your sample, right? So in regard to that, for all properties for which you know their distribution in the population, you don't apply random or blind drawing. You can then really apply intentional preparation of the sample in regard to that property. And you also know that, for instance, there are so and so many so the income level of people in the population is such and such, distributed in such and such way, so you choose a similar distribution in your sample. If you do that, you speak of what is called a stratified sample. Stratified sample. But that, as I said, can only be done and should only be done if you have really safe knowledge about the distribution of the population. If you don't have safe knowledge, but base your stratification on your theoretical prejudgments or opinions, then this is not the right way to go. Right? Then you prepare your sample according to what you want to come out, what you want is the outcome of your result. So that would be then actually a statistical error, a methodological error. Okay. So this brings me to the last topic, sources of error in statistical methods. And there are two kinds of sources of error in statistical methods. One kind of error concerns the testing of hypotheses, and it has to do with failures of representativity. This is the first kind of error. And the second kind of error is an error in interpretation of statistical hypotheses. This concerns failures in regard to the causal interpretation of statistical correlations. I will speak about failures of causal interpretations soon. Now I speak about failures of methodological mistakes in testing hypotheses, which are typical failures errors of representativity. Okay. I give you some examples. Generally speaking, if you do an experiment where you test for the relevance of a factor, you have an A sample, you have a control sample, an A control sample. Both samples must be representative. That's a requirement. So here's one example. An impromptu survey on a political topic is conducted by telephone using only landlines. Is this representative or not? What would you say? Yeah.
I don't think so, since a lot of young people use only cell phones, and you can't.
Exactly.
So you have a sample that's biased towards older people who stay at home.
Precisely. So, if you're doing such an impromptu survey, like it's done by several television channels, right? Where you only use these landlines, you miss all mobile phones. And mobile phones are usually used by the younger generation, and they have, of course, typically different political attitudes than the older generation, statistically speaking, right, in a statistical average, right? And so that's a typical failure of representativity if you do it in that way. So all these examples which I give to you are actually happening in practice. Another practice, I know that from a familiar psychologist. A psychologist does an experiment on forms of partnerships, right? How is your partnership going on? How do you divide the housework or the work in your family and so on? An experiment on forms of partnership. She places an advertisement in the newspaper. Test persons make contact, they are registered, they are volunteering, and with those test persons which are volunteering, she makes the experiment. Representative or not? Yeah, but what can happen? I mean, what would you say?
Well, obviously, newspaper readers, right? So
newspaper readers, that is one factor.
It excludes other.
Yeah. But let's assume the newspaper is really fairly distributed.
Some newspaper readers might be more keen to take part in the study.
Exactly, that's a second important factor. Who is motivated to enter such a study? That's a really problem, and it takes time. Probably people, like typical people say, a female wife. The man is always occupied by at work. She's often alone. She's really not satisfied with her situation. She has time. She goes, right? But a person who is maybe whose relationship to his partner or her partner is really problematic, because he doesn't spend enough time to the relationship, because he's so involved in his work, in his profession, will probably not have time to go to this experiment, right? So it will be a very unrepresentative sample. Of course, the question is now, and that's one reason why often people get paid, right, for experiments. If you pay them, they have, of course, a certain motivation. You can compensate for that by paying people for taking part in the experiment. But then, if you you must not pay them too much, right? Because then only those people go to the experiment because they make money with that. When the poor people, people don't care about scientific studies at all. Do you go to that study? Why? Because I get 100 euros. Oh, well, these crazy questions, what do you write? Well, I don't read them. Just write yes, no, yes, no, yes, no, and that's it, right? I get 100 euros. Oh, I do the same, right? If you get test persons of that sort, then the result will be crazy too. So it's really, if you take it seriously. If you take this problem serious, then you see a representative study is not easy. It takes time, right? It's also well known that most of the studies which psychologists do and publish their results, the samples which you use are drawn from what? Do you know that?
University students.
Usually from psychology students. I know some university psychology departments which even make it obligatory for psychology students to enter at least 5 experiments in their study, So in that way they grant the psychologists to have always enough samples, test persons, and they get credit points for participating in experiments. Right? But of course, at least for some questions to be tested, a sample consisting only of psychology students will not be very representative, right? I mean, you must really think hard about whether this is a failure of representativity or not. So, you see already, to do a serious experiment where we really take care about criteria like representativity costs time and costs money. Here's another example. A sociologist sends out a questionnaire to discover more about how much housework is done by women. This case really happened. It was a sociologist which was working at the government, for the government. Yeah? It was hired by the government to find out how much housework is done by women in the city. So she sent out 100,000 of these questionnaires, and something like 10% came back. Even not 10, 5% were returned and filled out. And then she evaluated the questionnaires which came back. What you say about that?
Well, women who do a lot of housework probably don't have the time to fill it out.
Yes, exactly. So really crazy. So when I told that to the person, well, yeah, oh no, you're right. Yeah, but she didn't really think about that. Right? So the result was, of course, very deteriorated and very deviating from the true statistical situation in the population because of this totally unrepresentative method of sampling, right? Just evaluating those which came back. So really, to have statistical knowledge about these things is very important if you do experiments of that sort. Okay. Of course, there are even stronger mistakes possible. Stronger mistakes which more severe mistakes which you find in non-scientific books or practices like say esoteric healers. For instance, you find a lot of books about esoteric healing methods like the pendulum method, right? Pendulum healing, right? So such a natural healer guy describes in his book his success with 15 patients. He describes his 15 patients having certain diseases which were healed by the pendulum method. But he doesn't speak about any control sample at all. Maybe he had 300 patients in his career so far, and only in 15 cases of the 300 it worked. Right? So the mistake here is that there is no control sample at all. Right? That is this mistake is not done in scientific experiments, but the mistake to have no control sample is typical for non-scientific esoteric books or reports. Also, if you read those reports of that kind, you must be aware that you don't know what else the healer prescribed to his patient. Maybe he prescribed to him while he was doing his pendulum healing method. At the same time, he told his patient, you should eat healthier food, change your diet, make more sports, and maybe these were the factors who led to the success in this case of this person, and you don't know by reading this book. So this is also a thing which is important to know. So the method of the common sense method of supporting one's thesis by collecting positive examples is wrong. The scientific method tells you always need control groups where you have these negative examples, and then you have to compare how much success you would have reached without that factor, and only if there is a significant difference you can speak of a relevant correlation. Another thing is interesting, namely, even in science, certain biases seem to be unavoidable. There's a study of a guy called Ioannidis, about very serious studies in medicine. He found that 35% of experimental results about the effectiveness of certain medical drugs in serious medical journals have turned out to be false. 35%. 35% of correlations proclaimed there have later on be refuted. How is that possible? Because this experiment were designed very serious, and the explanation of this, which most philosophers of science would agree today, is it's because of two biases. You call it the positivity bias and the sensation bias. The positivity bias means that young scientists, in order to be successful in their career, have to publish a lot in high-ranked journals. And typically, what is published are positive results. So if you want to establish a certain correlation, say, between certain illnesses and your food habits, your consumption habits, then you make several experiments and say, in 2 of 3 you have a negative result, and in the third one you have a positive result, and you publish only the third one, the positive result, and you don't publish the negative results. And you can really prove by statistical methods, if you do that, proceed in that way, then the chance of publishing a correlation which in your sample was significant, but which is truly insignificant. So publishing a correlation which is by random outside of the 95% interval, right? So of publishing a 5% error as significant, the chance of doing this increases significantly, increases to a value of 35% or so. This means that 35% of studies published in that way really made the 5% mistake, right? Because all these negative results are left out. And this is the standard explanation why so many studies which are published in medical journals could not be replicated by other scientists later on, right? This is called the positivity bias. And the sensation bias is similar, where they go for very small effects as I explained to you before, by choosing very large samples, you go for very small effects, and then in this way, of course, the chance is increased that certain random fluctuations observed as kind of errors mistakenly taken for significant effects, right? Random fluctuations are mistakenly taken by you as significant effects. This is what is called the sensation bias. Okay. So this concludes the part about errors in statistical methods. If there are no more questions on this part, or are there? Some questions? No? So if there are no more questions on this part, I come now to the next part of my course. And the next part is now about the important topic, correlation and causality. Correlation and causality. So far, I spoke about the difficulty of confirming a hypothesis about a correlation in the population. So, let me choose another color here. So there we have a correlation between two variables A and C. Say the probability of C given A is increased by A by 20% or so. Now assume we really have established the correlation in a correct way. We did not make an error of representativity or something of that sort. The correlation is really there in the population. Can we infer from this something about causality? I mean, I already told there, if there is such a correlation, so you assume that the probability of C given A is much, much greater than the probability of C given not A. So A increases the probability of C. then what we can say is that A is relevant for C. A is positively relevant for C. We can also say that A is predictively relevant for C. So there is a reason, if you want to predict C, look about whether A is the case or not. That will increase your predictive success in predicting C. But can we infer from that alone that A is the cause of C? Of course we want to have causal knowledge. And of course we want to get somehow to knowledge about causes from observation of statistical correlations, right? Now one thing we can say, if there is no correlation between A and C, so if these were equal, then certainly A is not the cause of C. So predictive relevance is a necessary condition of causal relevance, but predictive relevance is not sufficient for causal relevance. In other way, correlation, true correlation is not sufficient, is necessary. True correlation is necessary for causal connection, but true correlation is not sufficient for causal correlation. This is what I want to explain to you now. And there are two reasons why correlation is not sufficient for causality. The first reason is there may be hidden, what you call hidden variables, third variables which you don't know. Therefore they are hidden, you don't know them. We didn't measure them. And they are responsible for the correlation. This is the first reason. And the second reason may be the problem of the direction. A correlation is always symmetric. That is also something which you should recall. So it holds that A is correlated with C exactly if C is correlated with A. So correlations are symmetric, but causality is asymmetric, right? Causality is asymmetric. One thing is the cause and the other thing is the effect, right? And not the other way around. But correlations are symmetric. You may also write it down in that way. If the probability of C given A is greater than the probability of C, this is the case exactly if the probability of A given C is greater than the probability of A. Right? So this is a statistical law. So correlations are symmetric, causation is asymmetric. This is the second reason why it is not possible to infer directly without background knowledge from a correlation to a causal relation. First, I speak about the first reason for the deviation of... first, I speak about the first reason of, let's call them non-causal correlations. Namely, hidden variables. Okay, hidden variables. Now, there are two kinds of hidden variables. The first kind of hidden variables are hidden common causes. Let me speak about that now. What is a hidden common cause? A hidden common cause has the following structure. You have two variables, A and B. In that case, I use the variables not A and C, but A and B now, right? They are correlated, and this correlation is depicted by this double arrow, this dotted double arrow for correlation, right? So this is your correlation. And you assume it is a true correlation, so the correlation is really there. But it's not due to a causal connection, so the single arrow, the unbroken single arrow represents direct causation or causation, right? There is no causation relation between A and B, but they are joint effects of a common cause, C, namely C. C causes A and C causes B, and this explains the correlation, right? Because C is correlated with A, so A is correlated with C because since C causes A, C is correlated with A, right? Therefore, by symmetry of correlation, A is correlated with C, and we assume that A does not in some way change the probability between C and B. So C is also correlated with B, so since A is correlated with C, C is correlated with B, and A is irrelevant for that correlation, you get that A is correlated with B, right? As a result of a common cause. Here's an example. The first example is the barometer case. It comes from Greenbaum. Obviously, the falling of the barometer reading, if the barometer drops, right, the barometer reading drops, this indicates the coming of a storm, right? So there's a correlation, and this correlation is used for measuring, for measuring and for weather forecasting. But obviously, the drop of the barometer reading is not the cause of the coming of the storm. I mean, that would be crazy. Although that the storm will come is not the cause of the drop of the barometer reading, because the storm will come, right? It's not here already. That would be crazy too. The future influences the past. There's a common cause between the two, namely the drop of the atmospheric pressure. So the drop in this pressure, C, causes B, causes the storm to come. Because if the pressure decreases, then, so to speak, the air, the atmosphere is moved towards the zone of the decreased pressure. This causes a kind of wind, a storm, and this is the cause of both that's going on. And C also causes a drop of the barometer, of course, because the barometer measures the pressure, and therefore you get a correlation between A and B. So this is what's going on, and this is called a situation of a common cause. See that in this situation, Herb Simon, it's a famous guy, called this a spurious correlation. But that was at a time when the people were not so much aware of the systematic difference between causality and correlation. This was a very empiricistic time. A spurious correlation. But that term is not correct, right? Because the correlation is really there. It's not correct to call it spurious correlation. It's a true correlation. What is spurious here is the causal interpretation of the correlation. So you should better call this situation a spurious causality. Right? Only really rigid empiricists can call that a spurious correlation, because they somehow still think causality can be reduced to correlations. But according to a moderately, so to speak, modern realistic viewpoint, that's not at all possible. And you see it from this example, right? There is a correlation between A and B, a true correlation, but there is no causal relation. On the simple reason that they are both effects of a common cause. It is as simple as that. Good. Let me give you another example. This example comes from Lazarsfeld. This was in the 60s, when the effect of hard and stressful working conditions on the workers was investigated by a lot of sociologists in the times when capitalism were criticized. This was in the times, when you had factories with production lines, this very intensive work in production lines. If you have worked sometime at the production lines, you are doing 8 hours, always the same hand movement, and it makes you somehow crazy. I mean, if you do it all the time, right? And so there were a lot of workers who had certain mental health problems. But of course, the employers didn't want this to be true. They said, well, the mental health problems of the workers have very different reasons. We are not the culprits. Well, our working place is fine. And then they made a study, and the study was that there was a correlation between the attitude of the workers to the employers, whether they moaned about the employers, right, a negative attitude, or whether they said, well, my employer and the working conditions are okay. There was a correlation between the attitude and their mental health. There was a correlation between those factors. And then the employer said, well, you see, those people who have mental health problems on very different reasons project their mental health problems now on us and moan about us, right? And those who have good mental health, they don't moan about us. So you see, we are not the culprits, they project their problems. They make us do the culprits, but we aren't, right? So, but then it turned out there is no causal connection between A and B, because it turned out that there is a common cause, C. Let me stress in the workplace. Namely, if you only investigate workers under good working conditions, the correlation between A and B breaks down, right? So there is no more correlation between the mental health and the attitude to the employer if you only investigate workers under good working conditions, right? They may still differ in some of the people working under non-stressful conditions may still have psychological problems, for instance depression or so, but those people do not have a negative attitude to the employer, right? And similarly, if you only investigate people under bad working conditions, then the correlation between A and B breaks down, because there are still some of those people are strong enough to go for that working condition. They don't have any psychological problems, but those people then also don't have a negative attitude to the employer, right? So the correlation breaks down. And actually, this is exactly the criterion for the detection of hidden common causes. I say here the detection of hidden variables because you will see soon this criterion does not only detect hidden common causes but also another kind of hidden variables about which I speak the next lecture, the next lesson. But so today let me speak about this criterion in implication of common causes. It is called the screening off condition and goes back to a person which I have mentioned quite often, Hans Reichenbach. The screening off condition tells you that if there is a correlation between A and B, like here, or like here, and it is a effect of a common cause C, then this correlation breaks down if you conditionalize it on fixed values of the variable C, of the common cause C. So this is not noted, this is denoted by this expression here. It's called the conditional correlation, the correlation between A and B, conditional on fixed values of the variable C. So if this correlation breaks down, then the correlation was the effect of a common cause and not the effect of a direct causal connection between A and B, right? And this is exactly the case here, right? If I investigate only workers under good working conditions, then the correlation between their attitude to the employer and their mental health breaks down. If I investigate only workers under bad working conditions, then the correlation breaks down too. So the correlation is due to the fact, right, that stress in the working place is the cause of the mental health of the workers and the cause of their attitude at the same time, of course. And this is, of course, a very different result than the earlier impression which the employers gave, namely that the mental health problems of the workers have some other causes and projected wrongly to the employer. So this is a nice example. And it shows you also, it tells you the example, how important it is if you read about a correlation in the newspaper to ask, is this really the result of a causal connection, or could it be, isn't it much more plausible that it is simply the result of a common cause, right? And if it's the result of a common cause, the situation is totally different. Let me give you another example. So, another example of a correlation which you will see. And so the frequency, you know there is the story about the storks who brings the newborn babies. You know this story? Yeah? The stork brings the babies, right? The newborns. So where there are more storks, there are more newborn babies, right? If this fairy tale should be true, then where you find more storks, there should be more newborn babies, right? So what do you say if I tell you that this is actually true? So there's a strong correlation between the frequency of storks and the frequency of newborn babies. You find the correlation. What do you say? There's actually this correlation story. But what does it mean? Do you really now believe that storks bring the babies? Or maybe the babies bring the storks, I don't know. But it's somehow crazy. But the correlation is true. It's not a mistake of sampling. There is a correlation. The more storks, the more newborn babies. Do you have an explanation, maybe?
I can try. I think the common cause is living in a rural area, since in a rural area you can find more storks. It maybe the population of humans there reproduce more compared to I don't know, an urban area.
So you hit the right answer. You have the right conjecture. That's really the common cause, and you can test the hypothesis that this is a true common cause by applying Reichenbach's criterion here, right? So the common cause is the urban versus rural area, right? In rural areas, of course, you know, people get more children in the rural areas than in the cities. The birth rate is much higher there, and also in the land, in the rural areas, there are more storks, and it's as simple as that, right? Because of this common cause, you have a correlation between the frequency of storks and the frequency of newborn babies. So you see, at this example, ultimately, that to take correlation, to interpret correlation immediately or unreflectedly as causal connections is just stupid, right? But unfortunately, this is often enough done in popular magazines when statistical findings are published in magazines, and even journalists make the mistake of immediately taking a correlation as a causal connection. I mean, they may make mistakes like this, right? I mean, in this case, it's so obvious that something must be wrong that you start thinking. But if you I will give you a lot of examples of that sort next time. All examples, actual true examples from newspaper. I will read you to them and you will think about that. But if you take a correlation without reflection about possibilities of hidden variables, without reflection as a causal connection, then you may make a lot of interpretation mistakes. And in particular, if politicians make these mistakes, right, they immediately come out with a reform, maybe, right, come out with a reform, well, increase the frequency of storks in the cities and drive the population rate higher by that means. It would be crazy, of course, because there is no causal connection. But if you don't realize the difference between correlation and causality, you might make mistakes of that sort, right? Okay. So, any questions so far? No? Everything clear? So, we have seen that spurious causal connections, so to speak, or non-causal correlations may be a result of common causes, and they may be detected by the condition of screening off. So the common cause screens off its two effects, which means that the correlation disappears if you conditionalize on fixed values of the common cause. Both on high values and in low values, right? On all disappears by conditionalizing on all possible values. So you may conditionalize on arbitrary chosen values. Okay, now there's a problem. The problem is that this screening off condition does not only detect common causes, it also applies to what is called intervening variables, or better speaking, to what is called intermediate causes. So if you have a screening off situation, you cannot be sure from the statistical information alone whether the situation is of that sort, common cause, or of that sort. This is called an intermediate cause, and I will speak about this situation next time. So far for today. Thank you.